Go ahead and start with chapter 6. Okay, so we have 2 chapters remaining before the end of the year. It's going to fly by, okay, at this point. We're going to do chapter 6, and then we're going to do chapter 7. And then after chapter 7, we'll be preparing for our final exam. I can't believe it's happening. Section 6.1, our first section, is an introduction to exponential growth and decay. And we'll be working in section 6.1 today, tomorrow, which is really Thursday for us because we have block scheduling, and then also on Friday. Okay. On Monday in class, we'll be doing like a lab or experiment with exponential growth and decay to kind of put some of those things to use in front of us with real objects. And then next week on Tuesday, we'll kind of shift gears and talk about a different section. But we'll be in section 1 for quite a while, a few days. So today it's really just an introduction into growth and decay. And I'm going to start off with like a definition of exponential growth and decay. And that begins with, what is an exponential function? What makes something an exponential function? So we're going to say in exponential functions, and this includes both growth and decay, the variable is in the exponent. So you have worked with functions previously where you had exponents. Some of you might remember like the very basic y equals x squared. And you might say, well, I've done exponential functions before because x squared has an exponent of 2. Okay. But we classified this in our families of functions. This is actually quadratic, because the exponent is always 2. In order to have something that's exponential, we should have the x in the the variable in the exponent. So we would switch that around, and instead of working with x squared, what we're going to be doing in our current chapter is something more like 2 to the x. Okay, so do you see the difference between exponential functions and something that just has an exponent? And the exponent is the variable. Now, to determine the difference between growth and decay is actually very easy if you know these 2 points. First of all, our basic model for an exponential growth or decay function is y equals a times b to the x. That represents growth whenever b is greater than 1. We use the same formula for exponential decay, y equals a times b to the x, but it's decay whenever b is less than 1 but greater than 0. So notice it'll always look the same, y equals a times b to the x. The only way you'll be able to tell whether it's growth or decay will be if you're focused on what the value of b is. Okay? And b is the number that is the base to the exponent. Okay, so it's whatever the exponent touches. There could be another number in front that represents our a. It's just a scalar, so it can stretch or shrink our graph based on whatever the value of a is, but b determines growth or decay. Now, what I want you to do really quickly is with your shoulder buddy, have a discussion. And what I want you to discuss with your shoulder buddy is the answer to this question. What values is b not allowed to be? Okay, so what are the values that b is never? Okay, if we wrote out the statement b is not or b is never blank, what would follow that based on the inequalities I gave you. So have a quick chat with your shoulder buddy. What values is B not allowed to be? Raise your hand if you can tell me one thing that B is not allowed to be. B is not... Who said that? Oh, Faith. You said B is not negative. She says it so quietly. Okay, I totally agree. The inequalities that I gave you restricted all the B's that were less than 1 to also be greater than 0. Therefore, B is never a negative number. Okay? A can be negative, the thing that you multiply in front, but B itself will always be positive. If it's negative, then it's not what we would call exponential function. Did you discuss anything else that B cannot be? Jackson, you guys said? B is not 0. You can imagine what a boring function we would have if B were 0, right? 0 raised to any exponent is 0, and then 0 times any A is 0. So that would just be boring and not cool to investigate. So B is not 0. Were there any other numbers that B is not allowed to be? One more. I would agree that we will not pick imaginary numbers. That's not the one that I'm looking for. So there's another, let me clarify my question. That was a good one, Eric. What's another real number that B is not allowed to be? What's that? 1. Yeah. Notice that 1 is included in the inequalities. But it has to be greater than 1 or less than 1, which means it's never actually equals to 1. And again, think about what kind of boring function you'd actually have right there. 1 to any exponent is 1. So it would just be 1 times A all the time, and it would always just be like y equals A, which is a constant function, which isn't exponential. It's a horizontal line. Okay. So those are some things just to kind of make note of in your notes. Be aware of that, and that will help you as you go forward, like when you see an exponential function, identifying what B is and then determining growth and decay. So next examples that I want to do is show you 4 different functions, and we're going to identify them without graphing them as exponential growth or exponential decay. We're going to use that stuff we just wrote down about what is the value of B. In order to determine if a function is growth or decay, you need to look at B. Because if B is greater than 1, you have growth. If B is less than 1 but greater than 0, you have decay. So you need to decide in those 4 functions which number is B and does that represent a growth or decay. So again, I'm going to give you a chance to talk over with your shoulder buddy. What is B? Is it growth or decay? Have that discussion now. Okay, so remember, in order to determine growth and decay, you don't even need a graph. You really just need to focus on B. All of these equations come in the form y equals a times b to the x. So you should be able to easily identify your values for B. This green marker doesn't work today. And B should always be the number that has the exponent on it. Okay. So, Justin, could you tell me what you guys said for y equals 0.5 times 1.4 to the x? Yeah. Growth, y.
Times 1.4 is greater than 1.
Yeah, 1.4 is greater than 1. Cool. Kyle, what did you guys say for f of x?
I thought B was among the instances.
So if you're looking at f of x now,
It's
it is decay y.
because the 1/4 is less than 1.
1/4 is stuck in between 0 and 1. Juliana, what about g of x? Why do you say growth? Because 5/4 is greater than 1. So anytime you have an improper fractions will be greater than 1, and hence our growth. And then Bailey, what do you guys say for h of x?
I said decay.
Because?
Because it's less than 1 greater than 2.
Oh, less than 1, greater than 0. So that's pretty easy, right? Once you know what b is. Okay. Remember, they always come in alphabetical order, a times b to the x. Okay? Or you can just decide, like, whatever the exponent is touching, that's b. Okay, well, moving right along, we're going to do a graph. And you have, like, some questions on your homework that were like the previous example, and then you have several questions in your homework that are similar to graphing. So graph this along with me in your notebook, and we'll do maybe on this one, we'll end up doing a little bit more work than we would normally do on our homework assignment, just because it's the first time we're graphing the exponential function. So we're going to be graphing y equals 2 to the x. That would be considered like the parent graph, the original shaped graph, for all exponential functions that have a base of 2. So like if you remember like a's, h's, and k's, we still have those numbers that can change graphs, and that would just be like the original parent function. There's a new parent function for everything that's base 3. So 3 to the x is different than 2 to the x, obviously, because it has a different base. Okay. On your homework assignment, I would like for you to make this table of values for each of your graphs. I'll say 4 is probably good for you. We'll end up doing a few more than 4 on this slide. But you can use the same x values that I use, -1, 0, 1, 2. And that should be sufficient. They'll be fairly easy to calculate without a calculator, and they'll give you a good graph. So what we need to do is we need to plug those x values in, get out our y values in our table, then we can plot the points. So we're going to do that. X equals -1, then what is y for y equals 2 to the x? You can just shout them out. If x is -1, it would be 1 over 2. Yeah, 1/2. Because it'd be like 1 over 2 to the first. 2 to the first is just 2. What about 2 to the 0? Agree or disagree? 0, 2. Well, then what's 2 to the first? Okay, let me jump to 0 for a second. What is 2 to the first? What is 2 squared? I'm going to go back to 2 to the 0. It's 1. Anything raised to the 0 is equal to 1. So you have to remember it's different than multiplication, right? It has a new rule. 0 exponent property says anything raised to the 0 is equal to 1. And hopefully like that kind of made sense because it goes from 1/2 to 2. So it's got to be somewhere in between there. Okay, let's plot those points. -1, 1/2, 0, 1, 1, 2, 2, 4. Nice thing about your homework is it is a worksheet today, so the graphs, the coordinate planes are provided for you. You just have to plot your points on the actual graphs. And I'll say this, that on your homework, those 4 points are probably good enough, and you know exactly what's going to happen, so you could draw your graph from there. But this is our first time graphing the exponential function, so maybe we need a little more info. So to get that more info, I'm just going to pick some extra x values. But I don't expect you to do this on all your problems on your homework. You certainly can if you're ever worried that you might not really know what the correct answer is. So I'm going to investigate what happens if x continues to increase in the positive direction. So let's say I went from 0 to 1 to 2. What if x is 3? What's y? 2 to the third. 8. 2 times 2 times 2. Are you okay, Skylar? Do I have something funny on there?
No. I was confused.
What if I use x equals 4? Justin says 16. What if I do x equals 5? Someone said 32. Okay. What would you say, like, from these numbers from like 0 up for x's? What's happening to y's? 1, 2, 4, 8, 16, 32. Just generally, how would you describe them? They're doubling. How else could you describe them besides just saying they double? Maybe a little less specific about them. They're growing. What do you mean by growing?
They're increasing in certain numbers. Their graph will be going up and positive.
Okay, so it just keeps increasing. So they're like, can I say getting bigger? Is that okay? Green marker is having issues today. And something else that's interesting, and we'll kind of try to focus on this in the coming days, is like as they're increasing, like Jackson said, they're increasing faster, aren't they? So if you think about like the rate of change in between the points here, we're just going up by 1, then we're going up by 2, then we're going up by 4, then we're going up by 8, then we're going up by 16. So we're increasing faster and faster, so getting bigger. I want to stay away from the word increasing, only because it will cause confusion to some later. But our numbers are doubling, they're getting bigger, and it's happening faster and faster. So I'm pretty much okay at this point saying from x equals 0 and to the right, that would be an okay shape of my graph. Like, it's just going up faster and faster, right? So, you know, like the next point is at 8, then the next point will be at 16, and the next point will be at 32, and it's getting bigger and bigger. Okay? And in fact, what if I said x was 100? 2 to the 100. I don't want an exact value here, but what would you say about the number for 2 to 100? So how would you describe that answer? It's a lot, okay? I like that. Okay, in our table, we don't even really need to know the exact number for 2 to the 100. We're just going to say it's a lot. Jackson, you seem to maybe be punching things in your calculator. Do you agree with that?
Yeah.
Okay, he says yes. Okay, so that kind of corresponds to what's happening to my graph, right? If I went over 100 spots, it would be really, really high. Okay, now, on the other side, let's figure out what's happening to the left of our graph. Let's do a new table of values, because I'm running out of room. And I stopped at -1, but I'm going to go backwards, and I'm going to put -2 there. And I think we did this in the warm-up. What is 2 to the -2? Oh, no, we didn't do 2 to the -2. We did 1/2 to the -2. What would 2 to the -2 be? 1/4. 1 over 2 squared. So we put a 1/4. What about 2 to the -3? One over 2 cubed. 1 over 8. -4. 1 over 16. -5. Noticing a pattern there? Yeah, you can relate back to these numbers over here. What's happening as we go further and further left? What would you describe about these numbers? 1/4, 1/8, 1/16, 1/32. They're getting smaller. And to kind of put another qualifier on there, they're getting smaller slower, right, as we go to the left. Like the amount that we go down is less and less each time. Okay, it gets smaller and smaller. So what if I did -100? Why do you say a little? Yeah, just because the other one was the opposite. Can we verify that it is a little? Okay, so thinking about the pattern that you noticed here. 1 over 4, 1 over 8, 1 over 16, 1 over 32. What would negative 100 give us? 1 over
Roughly.
a lot. Yeah, it's a big number. And what do you know about having 1 out of a lot of stuff? It's very little. So it is a little. In fact, it's very little. Okay? I'm going to write here 1 over a lot is almost 0. If I cut up a Snickers bar into 1 million pieces and hand them out to 1 million people, will they feel like they got anything from me? No, not at all. So it's almost nothing, but theoretically it's something. So when you draw the left side of your graph, you need to draw it so that you get closer, and I probably did cross the axis. You get closer and closer to the x-axis, but you never, I have to move that point. You never actually cross it. So in your notes, make sure you draw the rest of your graph. On the left side, you are going to do what I call hugging the x-axis. You get really, really close to it. You just follow the x-axis the whole time. That's what's going to happen. You're going to get closer and closer to 0. We can't even draw it. We're so close to 0. So we just draw it going there. Okay. Now, that produces for us something very special. And I want you to start marking this on your graphs for me. And you'll do this on your homework. This line, this x-axis, mark it with a dotted line so that we know that dotted line is a line I should not cross. My graph will not cross that line. That line has a special name. I'm going to label it here, then we're going to go to the next slide, which has the definition. This is called an asymptote. The P is silent. So you really just say asymptote. You don't have to say the P at all. asymptote. That is your asymptote. So going ahead, just kind of write this down in your notebook. The asymptote is a line that your graph approaches but never touches. You're going to get really close, but you're never actually going to touch it. I do have a little disclaimer there. That's what my asterisk is for. We shouldn't run into this issue. Not even in our next chapter, which is most often the chapter where this happens. It's rational functions. But it is possible in rational functions to have an asymptote that your graph crosses. But it does it in the middle of your graph. So I'm putting a little asterisk here to say we're never going to touch the asymptote, or we're going to approach the asymptote. And really, mathematically, we mean that happens on the far left or the far right side of the graph. But somewhere in the middle, we might actually end up crossing the asymptote. Now again, we are not going to run into this issue. So for this particular class, this particular chapter, we know we're never going to cross it. But going forward, some of you might be taking Algebra 3 next year. You'll work with functions where there are asymptotes that you do cross. You just go back to it on the far right or far left of the graph. Okay. So I'm actually going to go back to our previous graph, and we're going to label 3 things: domain, range, and asymptote. We're going to label them nicely. Okay, so I'm going to do that underneath my graph. You can go back in your notes to that area. And we're going to label domain, range, and asymptote. Domains are all of your x's. So think about all the x's we put into the table of value. Was there any kind of x that we weren't allowed to put in? I don't think so. We could do any x value we wanted. So we're going to say the domain is all real numbers. X equals all real numbers. Do you remember my double-sided R for all real numbers? It's been a while since we saw it. Okay. And domain for all exponential functions is always all real numbers. So this should be the same for all your problems on your graph or on your assignment. Range is not x, range is y. So think about all the y's on the graph. Does your graph show up everywhere up and down? Is there a graph everywhere? Skylar, you're saying, heck no. There's no graph down below the asymptote, right? So how could you describe the y's where your asymptote or where your graph shows up? Y's, where are they? Greater than 0. Notice we don't include the or equals to because we know that 1 over a lot is still a little, and so we never actually have 0. And then the asymptote is that horizontal line that is the x-axis. It should be y equals 0. That's the thing that you're never allowed to touch. So the range is connected to the asymptote. Now, two things will always be the same for you. The domain will always be all real numbers. The asymptote in this section will always be y equals 0 because we don't have any vertical shifts up or down. Okay. Range can change. It can be greater than 0. It can also be less than 0 if the graph gets flipped over the asymptote. Does anybody remember what makes graphs flip over a horizontal line? So like if you think about y equals x squared, it's a parabola that opens up. What made the parabola open down? If there was a negative in the front. So if your a value is a negative number, you're going to plug into your table of values and you're going to see that all your points show up underneath your asymptote, and then you would say y is less than 0. And so your range can change, especially if you have a negative a value. Okay. Does anybody have any questions on that graph? I want to show you one more. And we're just going to switch it up. Instead of doing y to the 2x, we're going to do y equals 1/2 dx. Okay. So, things you want to do on your homework. Fill out the table of values. X equals -1, 0, 1, 2 should be sufficient for all your problems. I'll give you a minute to kind of fill in the table of values as you think it should be, then I'll fill out mine and we'll see if we agree. So what is 1/2 to the -1? It's 1/2 to the 0, 1/2 to the first, 1/2 squared, check your answers with mine. Do you agree? 1/2 to the -1. Well, that would flip what it's touching. So it would become 2 over 1 to the first, which is just 2 over 1 or 2. Anything raised to the 0 is always equal to 1. 1/2 to the first will be 1/2, and 1/2 squared, I think we did in the warm-up, is 1/4. Could you plot those 4 points? Sure. Without any trouble. So plot them, and they give 1, 2, 0, 1, 1/2, 1/4. And this is what I'm saying. Now that you kind of saw what happened when we did that like extended table, can you picture how the graph might look here? with just those 4 points. If I connect my y-intercept to this point, -1, 2, I'm probably just going to keep going up, right? That's like really the only natural thing for my pencil to do, to keep a nice smooth curve. And then if I take my y-intercept forward to the positive x values that I plotted, those are the ones that are getting really, really close to the x-axis. So how might you describe this graph compared to the other graph? Yeah, you might say it's like going the opposite direction. It's sort of like reflected this time over a y-axis. It's high on the other side. It's lower on the other side, something like that. So then we'll draw in our asymptote. Remember, our asymptote is always going to be the same. And then we'll identify domain, range, and asymptote. So your directions on your homework will ask you to do these 3 things too. Bless you. So domain would be x equals all real numbers. That will always be true for exponential functions because there's no rules about exponents. Range, notice that your graph is always showing up above the asymptote, so y's that are greater than 0, and the asymptote is y equals 0. Just to kind of give you an idea, when does this change, right? That whole range piece. We talked about the idea like if we flip it over the horizontal axis, that would cause it to be underneath the asymptote, and then we would say y is less than. And negatives will do that. So if I just put a negative at the very front, then if I were to fill out my table would be almost exactly the same. Like when I put in -1 for x, I'll flip it and get 2, but then there'll be a negative in front of it. So then it would be -2, -1, -1/2, -1/4. Everything just gets multiplied by this -1 that's in front of my function. And then if I were to plot those points, I would have this graph that shows up underneath my asymptote. Okay? So the domain would still be all real numbers. My range would have to change to be less than 0. My asymptote would still be 0. And these go to that. So this is a big thing that we're going to talk about going forward. Both of these are actually exponential decay because the b value is less than 1. The b value is 1/2 in both of them. But something that's really confusing to a lot of people is decay does not mean decrease. The black graph is decreasing from left to right, but the blue graph is increasing from left to right. So things can be exponential decay even if they're increasing. It means that the rate of change is decreasing as you move to the right. So it gets like more like horizontal as you go to the right and it approaches its asymptote. So that's a concept we're going to work on building as we go through these next 3 days of section 6.1. Okay, this idea that decay does not mean decrease, growth does not mean increase in terms of the actual graph itself. Okay, so kind of be aware of that and be thinking about that. Your homework assignment is going to be this worksheet, and I want to make sure I get this to you.